Alright, hopefully this worked. Hopefully this worked. I have no idea whether or not it's going to or not. I mean, I think it will. I'm pretty confident that it will. But it has been a morning, to say the least. My apologies for those of you tuning in, both now and much later on, whenever you watch this. Yeah, it's just been a crazy time. I cannot get my jump drive, my thumb drive, to connect to my computer for some reason right now. I'm having trouble because I had things that I had downloaded on there that I was going to share with you this morning, and now it looks like I'm just going to have to quickly redo what I wanted to do as you guys are filing in or something like that. Yeah, my daughter decided to wake up at 3:30 in the morning and not go back to sleep. What's up with that? I don't get that at all. But that's what we're dealing with this morning, you know. Hold on. AP stuff. I'm about to upload a PDF for you guys up to the Google Classroom stream. I was going to make sure I title it correctly. Come on, you. And save that. Go to the stream. PDF for today. Add the file. Yep, since my USB is not recognized, I'll have to reformat that. Post. Boom. Excellent. There we are. Okay, so for those of you that are here with us this morning, obviously, like I said in the comment that I left last night, they're not requiring us to take attendance. You are not required to be in this live streams right now. So hey, thank you for being here. But do me two favors. Number one, just put a comment into the chat just so I can see like who's here. Just because I like to know who I'm talking to. Number one. Number two, please let me know that the PDF that I just posted to Google Classroom, please make sure that it is that it uploaded correctly. It should be a PDF that has like 3 pages to it, and this is mainly what I want to be focusing on this morning, obviously. So throw a comment into a chat. Let me just see who's here. Again, I'm not taking attendance because they're not requiring us to take attendance. But I'm just, I don't know. It's been a crazy morning. I've pretty much been awake since 3:30, and yeah. And my kid's school got canceled, but he's not required to do school. Yay! Thank you for that. Thank you. Good morning. Oh goodness, what is on here? Do I have any messages up here? No, I don't have any messages up here. Good morning, guys. So I'm gonna open up the PDF that I just posted, and I am going to just very briefly show it on the screen. I'm going to very briefly show it on the screen so that I can make sure I get the right one here, so that I can just kind of walk you through that. Again, my brain is done right now. So look, there I am, and look, I'm in a hoodie right now. I'm so tired, I forgot to put on a shirt and tie. But such is the life of having, a 2-year-old that doesn't want to sleep. So, but again, thank you guys for being here this morning. Hold on, let me close that. Which one am I on? There we go. I just wanted to get back to the chat there. There y'all are. I can see y'all in there. Good. So, the PDF that I just sent you guys, I'm going to try and zoom in just a little bit here. Boom, there we go. I know it says test at the top. This is the review. what you have in front of you is just what I'm going to be reviewing for the next little bit of time. Obviously, I'm not going to keep you terribly long, but there's 10 multiple choice questions, which I'm just going to kind of walk you through step by step. There are some free response questions here, in which I do have my calculator, and I can obviously do the top down to kind of write out some stuff. They have some free response with some printouts that I want to go over. And when all is said and done, I am going to be providing you guys with an answer key at the very least, so that you can see exactly what we're dealing with. Let me see if I can print this out. Hold on. My printer on? I think my printer's on. I hope printer's on. I don't know how computers work. Oh, there's the print button. Print. Goodness gracious. Okay, print. Save print output? No, I just want you to print. Print to my printer. Oh, goodness gracious. Okay, fine. It's not going to connect, so forget that. I'm just going to go through the questions one at a time here then. And we'll kind of do that from there. So number one. All but one of these statements contains a mistake, which could be true. Now, I love multiple choice questions. Again, they make up half of your AP test. And they can be the scourge of your day because you have an hour and a half with 40 questions. So let's just kind of go through them one at a time. The correlation between a football player's weight and the position he plays is 0.54. Now, I'm going to stop right there. That is clearly not correct. The correlation between a football player's weight and the position he plays. The position that he plays is categorical data. There's definitely categorical data. As a result, boom, it can't be true. B, the correlation between the amount of fertilizer and the yield of beans. Yield of beans would be like the amount of beans that are produced from whatever crop, I guess, is 0.42. That seems pretty legit. But I'm going to read the rest of them just for the sake of argument. C, the correlation between a car's length and its fuel efficiency is 0.71 miles per gallon. That one can't be true. And the reason why that one cannot be true is because they put the correlation coefficient 0.71 with units, miles per gallon. That cannot happen. There are no units on the correlation coefficient. D, there is a high correlation 1.09. I'm not even going to read the rest of it. Correlation, as we've talked about, can only be measured between -1 and +1. Clearly, you can't have 1.09. And then there is a correlation of 0.63 between gender and political party. Again, categorical data cannot happen. The answer has to be B. So, haha, excellent. Now, just for the sake of argument, if you have a question that pops up into your head, I'm going to be periodically looking at the chat on the side right there. In fact, I probably should have the chat open on my, I got the laptop right here too. You know, the laptop from school. I'm going to have that open as well while I'm doing this. So if you do have any questions, that means that I don't have to check the chat. If I don't check the chat, I'm sorry, I don't have to check it on my computer. I can check it on the Chromebook. Anyway, let's go back to number two. Number two, residuals are possible models not explored by the researcher. Variation in the data that is explained by the model. Sounds like R squared. The difference between observed responses and values predicted by the model. Of course, that is just the pure definition as to what a residual is. Just for the sake of argument, let me just take a quick peek. Data collected from individuals that is not consistent with the rest of the group. No. And then none of these. I mean, yeah. Obviously, in this instance, the answer should be C. And it is. Happy day. Ooh, number three, influential points. Now we're getting busy. Which statement about influential points is true? Let me just mute this and go into this. Come on, you. View live in the control room. I'm trying to open it up on my computer now. Haha, there y'all are. Excellent. So I can take a peek at that whenever I need to. Cool. Removal of an influential point changes the regression line. Data points that are outliers in the horizontal direction are more likely to be influential than points that are outliers in the vertical direction. Influential points have large residuals. Now, this is worth it to kind of draw out a little bit. Let me just make sure. There we go. Let me just make sure that I get my correct marker here. Where's my marker? Yeah, I had a whole box of them. There's one. Okay. So, influential points. I'm going to flip to top down. There we go. Cool, 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 cool. And I'm just going to draw an example of an influential point. Now, the definition of an influential point is a data point whose, if you removed it from the data, then it would drastically change the slope of the line of best fit. This is the definition of an influential point. In contrast, a leverage point has an x value that is far from x bar. Now, it is possible that you could be an influential point and a leverage point at the same time. That is entirely possible. For example, if I had this set of data right here, and then my extra data point was over here, this data point would definitely be leverage in the sense that it is far from x bar. But it could also be considered influential because this is what the line of best fit would be without that point. But with it, it drags that slope down and drastically changes what it is supposed to be. There we go. I gotta keep reminding myself to double check the chat every now and then. If I had multiple monitors up here, man, this whole day would be awesome. Anyway, let me just check real quick what the answers were on that thing. Or not the answers, I'm sorry. There it is. Good. Removal of an influential point changes the regression line. I mean, that's fair. That's fair. If you removed an influential point, it could definitely drastically change the slope, so we would change the regression line itself. So that's fair, that's true. Data points that are outliers in the horizontal direction are more likely to be influential than points that are outliers in the vertical direction. It's a weird way of saying it, but that is a true statement. That is a true statement. Let me kind of, again, exemplify that here. I mean, clearly, if I had a data point that was down here, I'm not going to draw it, but if I had a data point that was down here, that would greatly influence it. And it's obviously in the vertical direction. But I guess the general idea is that if you had data that was basically in this general region, then it's less likely that you would have a point that was all the way down here. Much less likely. Like, that wouldn't be consistent with the data whatsoever. And same thing for like all the way up here. But it is entirely possible that you could have like a point like maybe here or something like that. You know, like not necessarily extrapolation depending on how much data was collected. That's a really weird way of wording that. Not a huge fan of that statement, but that statement is technically true, that second statement. And then influential points have large residuals. Not necessarily, they could. Influential points could have large residuals, but they don't have to have large residuals. In fact, like for example, with these points right here, you can't see it, I gotta go top down, top down. If the line of best fit were then changed to this because of those points, these points would not have very large residuals compared to some of the other ones up here. Like this one, for example, versus, you know, this one. I mean, obviously this one's a little bit bigger, but then this one has a small one, you know. All things considered, I would say that the answer is B. Let me double check that, actually. Yeah, it is B. Look at that, I was right. I gotta sneeze. Hold on, let's see if I can mute myself or take my mic off. It has been a morning. My goodness gracious. Anyway. And my cat is in the room. I really hope he doesn't come over here. Alright, let's take a look at number 4 then. Which is true. Random scatter in the residuals indicates a model with high predictive power. That's not what a random scatter in the residuals means. A random scatter in the residuals indicates that a linear model is appropriate, not that it has quote-unquote high predictive power. Yeah, no, that doesn't work. Number 2, if two variables are very strongly associated, then the correlation between them would be near 1 and -1. Now, this is something that I saw on some of your guys' responses when you didn't necessarily talk about the form of the scatter plot. A lot of you talked about the strength and the direction, but you never talked about the form. In that second statement, it's a very specific statement. If two variables are very strongly associated, it never said it was linear. It never said it was linear. It just said that they were very strongly associated. It could be quadratic. It could be exponential. It could be anything else. If it's very strongly associated, it might have a correlation at 0 if it's a quadratic association. So that statement can't be true either. Number 3, the higher the correlation between two variables, the more likely the association is based on cause and effect. Correlation does not equal causation. Absolutely not. The answer is none of them. None of them are true. Shh, silly little thing there. It's none of them that are true. Anyway. 5 and 6 kind of go together, just because it's similar, but we'll get into that. Anyway, a company's sales increase by the same amount each year. The same amount each year, so it's like 10,000, 20,000, 30,000, or something like that. The sales grow like that every single year. Yeah, it has to be linear if you're kind of thinking about that. Constant rate of change, linear. Number 6, another company's sale increased by the same percent each year. Ooh. For those of you, again, who have taken Algebra 2, you should remember the concepts of exponential growth and what that equation looks like, I should say. So yeah, if it's the same percent each year, it's got to be exponential. Number 7, a scatter plot a scatter plot of 1 over square root of y versus x shows a strong positive linear pattern. It is probably true that. Okay. Here's the rationale for this problem. If you're looking at a scatter plot of 1 over the square root of y versus x, then most likely you have attempted to re-express the data, where you went down the ladder of powers and determined that 1 over the square root of y gave you the best looking residual plot. That's that process where we would go through and we would rerun the linreg with L1 and L3, and then check the residual again over and over just to see, okay, which one gave us the most scattered residual, and then from there we would be able to write out the equation. So what they're saying is they re-expressed the data, they used 1 over the square root of y, and they got a strong linear pattern. Because they re-expressed it, it is probably true that in its original form of x versus y, that it did not show a linear pattern. Maybe it showed a very prominent curve or whatever it ends up being. Let's just take a look. If you look at the choices A, B, well, A, B, C, yeah, all of them basically are talking about x versus y. They're talking about the original one. So it's probably true that A, the correlation between x and y is near 1. Probably not. I mean, it could be. It could be, but probably not. B, the scatter plot of y versus x, the original, also shows a linear pattern. Probably not. That's probably why we needed to re-express our data in the first place. I mean, it could show a linear pattern, but again, the residual plot probably revealed the truth. C, the residual plot for regression shows a curved pattern. Probably. It's probably true. And it even says that in the question. It is probably true, not that it is true. But the reason why you had to re-express the data is because the residual plot showed a pattern. So you had to re-express it. I'm pretty sure it's C. I'm right, it is C. But D, large values of x are associated with large values of y. Again, not necessarily. I mean, it could be, but probably not. And then accurate predictions can be made for y even if extrapolation is involved. Again, extrapolation. Take it with a grain of salt. Extrapolation is not always trustworthy. I mean, it could be trustworthy. Let me look at the chat again. Hey, guys in the chat. Anyway, let me scroll down a little bit more. 8 and 9. There we go. Number 8. It's easy to measure the circumference of a tree's trunk, but not so easy to measure its height. Facts. Forecasters developed a model of ponderosa pines that they use to predict the tree's height in feet from the circumference of its trunk in inches using that. Now this, I referenced this in class the other day. But I talked about the general idea of the natural logarithm possibly playing a role, number one. And number two, the fact that you may see an equation in the future where they re-expressed not only the y's, but also the x's. So in this particular instance, in this model, they have ln of h hat, which is your y. They re-express the y's, equals negative 1.2 plus 1.4 times ln of c, the circumference, that is the x value. They re-express the x values too. Interesting. Okay, I haven't even read the question. A lumberjack finds a tree with a circumference of 60 inches. How tall does this model estimate the tree to be? All right. Let me write something down, and then I'll go to my top-down model. H hat equals negative 1.2 plus 1.4 ln of c. And they're saying 60 inches is their circumference, so ln of h hat. And yes, they did say that the circumference was measured in inches and that the height would be measured in feet. So I'm going to assume that they kept it in those units in the original form. Let me change the top down real quick. There we go. Changing the top down. Okay. So I'm looking at top down. Let's just see what this thing does. Negative 1.2 plus 1.4 natural log of 60. Boom. It spits out the following. 4.532. Okay. In order to get the natural log off of the h hat, because it's a natural log, again, this goes back to your Algebra 2 skills. I did not teach you Algebra 2. I wish I did. Simply because then I would have known exactly what you've been taught. But I'm going to assume, based on my conversations with Miss Betty and the other Algebra 2 teachers, if you happen to take CP in a previous year, I'm going to assume that you have been taught this at one point or another. It's a natural log. So e to the power of 4.532 spits out a predicted height of 92.94 feet. I believe that works. Double check something here. Where's the actual choices? Boom. Interesting. Am I right? Oh, snap, I'm right. Huh. Now, mind you, it is feet, but there we go. Somebody might accidentally divide it by 12, thinking they had to convert it. No, they didn't give you that choice. I was trying to see if they gave you one of the choices, but yeah, it's 93 feet. Look at that. Let me switch back to top down real quick and show you that there. Chapow. It's pretty solid. I like that. I really like that problem. Out of the way. Out of the way. There we go. I don't know. That's a fun problem. I'm just thinking of a tree that's 93 feet tall. It's got like a redwood or some junk like that. Anyway, back to the problem. Woohoo! Number 9. Two variables that are actually not related to each other may nonetheless have a very high correlation. Yeah, I've seen that. Stork's babies. Because they both result from some other, possibly hidden, factor. This is an example of. Now, I haven't given you this formal definition. I kind of glossed over it and kind of mentioned it verbally a few times, especially since we started talking about storks and babies and whatnot. But yeah, this is a lurking variable. It's a lurking variable. When it comes to correlations, they refer to them as lurking variables, something that that's hidden that could possibly affect the reason why it's highly correlated. When you're dealing with experiments, you're mainly dealing with confounding variables, something within the experimental design that could possibly explain the results that you got, or could possibly, not shield, but mask the results that you got, or something along those lines. But yeah, lurking variable, they mainly, we referred to them when we dealt with observational studies. The fact that you can find that two things, like, oh, look, these things are related. Yeah, but even though they found that they were related, it doesn't necessarily mean that it could be a lurking variable. All right, let me flip down on this. Here we go. Click, 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 boom. All right. If the point in the upper right corner of the scatter plot, I'll move my mouse there. Wait, no, you can't see where my mouse is. Hopefully you can see it now. Whatever, you can see it. In the upper right-hand corner, I'm so tired, of the scatter plot is removed from the data set, what will happen to the slope of the line of best fit? Okay. So I'm trying to figure out how I'm going to show this, especially considering the fact that I can't just put my pen down on a piece of paper because I can't print this stuff out right now. I logged off the computer for some reason. Let's talk about it like this. If you can imagine what the line of best fit would be with that point and without that point, hopefully, I don't know if you can see this, with the point, the slope would be a little bit more elevated because of that outlier, or that supposed outlier. Are they calling it an outlier? Yeah, they're not calling it an outlier. But without that point, if you remove that point, then the slope would be less steep. The slope would be less steep. So what would it do to the slope? It would cause the slope to decrease. I'm not looking at the choices yet, but they also ask about R. If you remove that point, then the line of best fit would show would go through a much more representative cluster. Thus, the correlation would be stronger if you remove that point. So R would go up. So slope would go down, R would go up. Slope would go down, R would go up. It's got to be D. Yay, we did it. It's D. Huzzah. It is D. I knew it was D. Whatever. All right. Sometimes they'll do that too, where they'll have you kind of like visualize, like, okay, what would happen in this particular situation? Oh, number 11. A company manufactures a polypropylene rope with 6 different sizes. To assess the strength of the ropes, they test 2 samples of each size to see how much force the ropes will hold without breaking. The table shows the results of the tests. We want to create a model for predicting the breaking strength from the diameter of the rope. Okay. Interesting. Find a model that uses re-expressed data to straighten the scatter plot. The company manufactures probably 6 different sizes to assess the strength of the ropes. They test 2 samples of each size. Interesting. I like that. I really do like that, actually. So how many data points do we have? Technically, we have like 12 data points. Yeah, 12 data points. Here, let me enter something into my calculator real quick. And I'll show you what I'm referring to. Come on, you. 10. This is a really weird way of putting it. 753. I'll show you, once I type this in, it'll be much easier to see what I've done here. Okay, double checking all my data. Okay, let's just see what happens. Let me do the top down. Top down, there we go. So, and I'll go back to the chart in a minute to kind of justify what I did here. But what I did was I did 4,60 and 4,76, for example. Because if you look at the information that they gave you, they tested a diameter of 4 with 2 different ropes. They tested it twice. And how much force they could hold without breaking. So it could hold 60 and then it broke, and then it held 76 and then it broke. So it's like 2 different ropes. So it's 2 different data points right there, which is why I typed them in like that. There we go. And then I did that for everything down beneath. Okay. Let me just look at the original scatter plot. Zoom 9 it. What do you mean syntax? Oh, I got a bunch of stuff in there. Zoom 9 it. Okay. I mean, clearly it already looks curved. Diagnostics on. There we go. Let's run a linreg. No, not you. Linreg. Boom. Zoom 9 it. No, I gotta look at the residual plot. Residual plot. Zoom 9 it. Clearly that's not gonna work. Clearly there's a distinct pattern in the residual plot, so I'm going to have to re-express my data. Re-expressing my data. Now, the way that I'm doing this, I'm pretty proficient in typing this stuff in. I mean, not terribly proficient, but pretty proficient in typing this stuff in. There's the residual plot with squaring all the y values. So going down the ladder of powers, go 2, 1, and then a half. So I'm going to have to do square root now. But, I mean, once you get the hang of this, it's not that difficult to kind of re-express all this stuff. Zoom 9. Ho-ho, there we go. Nice. Square root function. Let me check the answer key real quick, just to make sure that I'm not... Yeah, square root. There it is. Nice. I didn't want to keep going if I didn't have to. Well, yeah, that square root thing's totally going to work there. Huzzah! Paper. I got paper here. There we go. So, going back to this, let's see. I re-expressed it using square roots, and be 1.373 x plus 2.637 if I had to round that. Yeah, that looks about right. Yeah. And of course, I would, let me see what the question's actually saying. Here we go. It says, find the model that uses the re-expressed data to straighten the scatter plot. So maybe I'd say something along the lines of x's diameter measured in millimeters, and maybe I'd say that y, maybe even like y hat or whatever, it says kilogram, so it's the force that they can hold. What's that thing say down here? Yeah, whatever. All right, so the strength, strength in kilograms. Something along those lines. Nice. The company is thinking of introducing a new 25mm rope. How strong should it be? Write a sentence in context based on one of your models. Based on one of your models. They're referring to one of your models. I got one model. Oh, that's hilarious. Sorry, I'm just taking a peek at the answer key, and the answer key doesn't even have an answer for B. It's just blank. That's just flat out ridiculous. Anyway, whatever. Let's keep going. I'm just gonna do it. 25mm. I can predict that. All I gotta do is plug in. That's the wide shot. Anyway, 25 millimeters. I just got to plug that junk in right here. 1.373 times 25 plus 2.637. Boom. It should hold a strength of 36.962 kilograms. Now, I want to emphasize the fact that that number is predicted. It is a predicted number. It's not that it will hold it, but it is a predicted number. More importantly, it is an extrapolated number. I want to emphasize that. It is an extrapolated number. Now, extrapolation doesn't necessarily mean that you just completely ignore it. You don't just completely ignore extrapolation, but it should be taken with a grain of salt. The fact that extrapolation may not be completely trustworthy. So you can make that prediction, but then caution whoever's reading it. It's extrapolation, so perhaps it's not the most accurate. Something along those lines. Oh, there is no C. That's weird. That's just so weird. I just realized something, and nobody pointed it out to me. Unless you did in the chat. Hold on, let me double check the chat. Nope. No one pointed it out to me. I'm going to go back to my top-down menu. We re-expressed our data. We re-expressed our data. The square root of y hat equals that. Which means we have to square the answer that we got in order to get the actual answer. Well, yeah, 1/9. I knew I didn't circle it for a reason, but I don't know why I wrote kilograms. That makes me sad. But yeah, we re-expressed our data, and since we re-expressed our data, we were using this re-expressed equation. In order to get the actual answer, we had to square it in order to get that y by itself. Fun. Fun stuff. All right. Let me look at the next one. Oh, goodness. All right. Number 12. Ooh, number 12. Okay. Suppose the correlation between SAT verbal scores and math scores. You can't see it. I mean, you can at home, but there it is. Suppose that the correlation between verbal scores and math scores is 0.57, and that the scores are normally distributed. Ooh, normally distributed. If a student's verbal score places her in the 90th percentile, at what percentile would you predict her math score to be? Ooh. Let me go back to my top-down menu for a moment. Check this out. I wrote that into my notes a long time ago. I wrote that into my notes, I don't know, like several class periods ago. But just the general idea that you could re-express everything into z-scores. And if you re-expressed everything into z-scores, then this is what the relationship would be between the average of the z-scores, I should say. It's really interesting, to say the least. Now, what the question's saying is they're saying they want to predict math from verbal. So in reality, it's like math from verbal, some junk like that. They say that they scored in the 90th percentile for verbal. In the 90th percentile for verbal. Let me double check that real quick. Yeah, 90th percentile for verbal. So check this junk out. Inverse norm. Oh, what am I doing? I didn't hit enter. That is the z-score for verbal, 1.28 approximately. And they tell you in the problem that the R value, the correlation coefficient, is 0.57. Which means that the z-score for math is 0.7, well, top down, is 0.73 approximately. But that's not our answer. That is not our answer. Because the question, I'll go back and forth, is saying at what percentile would you expect her math score to be? That is not the percentile of her math score. That is the z-score of her math score. If you were to kind of visualize this on a normal distribution, here's the average, and approximately here is where the math z-score would be, right there. And if we were to figure out the percentile, this is something that obviously we're going to need to recognize how to do from previous chapters. But if we were to recognize what the z-score would be, or I'm sorry, the z-score, the percentile, whatever, I'm just typing in all these numbers. I'm going to go normal CDF, low number, really big negative number, comma, the z-score. It is the 76.7th percentile. Yep. They wrote 76 in the thing here because they rounded a bit more than I did. I didn't round as much. Finally, if I go back to, there it is, if I go back to right here, whoo-hoo, you have this big old stinking problem, number 13. And this is what we're going to wrap up with today. Doctors studying how the human body assimilates medication inject some patients with penicillin and then monitor the concentration of the drug in the patient's blood for 7 hours. Weird. The data are shown in the scatter plot. First, they tried to fit a linear model. The regression analysis and residual plots are shown. So to the right, I can see the residual plot clearly showing a pattern. Ooh, a linear model may not be appropriate. They got an R squared. Okay, cool. All right. Interesting. Right here. If you can see that. Right, I don't know. I'm trying to show where my mouse is. I don't know if it's actually showing up on the thing. I really hope it is. Let's see what it's doing here. It kind of is a little bit. Yeah, okay, you can kind of see that. All right, good for me. So right here, I'm kind of trying to show where my mouse is. These are the two numbers that we're really interested in. And the R squared up here is what we're really interested in. In terms of variable and coefficient, constant versus time, constant your y-intercept, time is your slope. They want to know what is the correlation between time and concentration, and they give you an R squared. Let me just write this down, actually. I'm going to write this down, and then I'm going to flip my thing over. R squared equals 90.8%. I know that my y-intercept is 40.3266, and my slope is negative 5.95956. I may have to speed up a little bit because I know I'm running short of time. Change this to top down. Top down. First, they wanted to know the R. So I'm going to square root 0.908, and I'm going to get that. But that is not exactly my R, because my R could be positive or negative. And because the slope is negative, that means that my correlation coefficient, I'll round this, is definitely negative. Oh, again, wide shot, top down. No, website. There we go, nailed it. Using this model, estimate what the concentration of penicillin will be after 4 hours. Okay. The concentration of penicillin after 4 hours. All right. Again, this is using the linear model that should not be used because the residual plot clearly showed that it shouldn't be used. But after 4 hours, let's see, negative 5.95956 times 4, 40.3266. I feel like I have to sneeze again. But yeah, after 4 hours, 16 point, I'm going to round it 5. But 16.5 what? It said the concentration. Go back. It said the concentration. Estimate what the concentration would be. The concentration is measured in units per cc. Oh, you can't see what I'm writing. Whatever. Top down. There we go. Units per cc. Part C. Is the estimate likely to be accurate, too high, or too low? Is that estimate likely to be accurate, too high, or too low? Interesting. Now, you can see based on the residual plot, that a lot of these, well, the data points are literally dipping below right there. It's just dipping below. Oh, nice. And they have on the x-axis, it says predicted C over T. Nice. Predicted C over T. That's weird. Sorry, I'm just looking at what this is saying. It says predicted C over T, but that's not really helping. Let's figure out what the residual... No, I can't figure out what the residual is. I mean, I can, but I can't. I'm looking... Oh, there it is right there. Okay, okay. Interesting. Go back to the actual thing. Then monitor the concentration of the drug in a patient's blood for 7 hours. Now, regardless of what the x-axis is, if they're monitoring it for 7 hours, then these data points represent all the data points from 0 hours to 7 hours. 4 hours would be approximately right in the middle. This is literally the rationale that you could use. Since they explained that they're monitoring it for 7 hours, this residual plot shows all the residuals from 0 hours to 7 hours. 4 hours would be somewhere in the middle. Thus, using this model, or no, I'm sorry, is the estimate likely to be accurate, too high or too low? And in this case, I would definitely say that it would be, well, they're not using the proper words. I'll finish up with this, but they're not using the proper words. Residual is observed minus predicted. Okay? A residual is observed minus predicted. And if you have scatter plot that looks like that, and I look at this point right here, okay? The prediction, which reminds you, this is the prediction, this is the observed. The prediction is too high. This data point would have a negative residual because the prediction is too high. Again, the prediction is in reference to the line itself. So if I go back to the question, is that estimate likely to be accurate? No, probably not. Too high or too low? The estimate. The estimate is the prediction. The estimate is the prediction. What really happened is the data point. So this thing would definitely be too high. The residuals are negative, definitely. The residuals are negative, but the estimate would be too high. Now, I do apologize. I am out of time. There are 2 more questions here. I am going to, in probably the next 10 to 15 minutes, because I have to do something for another class, but in the next 10 to 15 minutes, I am going to be posting the answer key to this review. I will also be posting, before the end of the workday today, an assessment for you to get done in regards to this unit that we have been covering on linear regression. I will be at my computer most of the day, obviously. I can take questions if you email me or send me a private comment or something along those lines. That'd be fantastic. The major would not be due until early next week. So I just want to make sure that we're all on the same page with that. I'll post these reminders, of course, in Google Classroom. Yeah, thank you guys for coming. Hope you had a good time. This is such a weird day. But I appreciate you guys all coming out, and I appreciate whoever ended up watching this later and watched the whole thing to the end. But I'm going to sign off. Go jump in the snow. Oops, sorry. Yeah. No snow. But have a good day. I'll see you guys later.